Now, the paper highlights 3 specific ways that this multi-head attention is utilized within the transformer architecture. Can you clarify those different applications?
Absolutely. First, you have encoder-decoder attention. Here, the queries come from the previous decoder layer, and the keys and values come from the output of the encoder. So this allows the decoder to focus on the relevant parts of that input sequence that was encoded by the encoder.
Okay.
Second, within the encoder, there are self-attention layers. In self-attention, the queries, keys, and values all come from the same place, the output of the previous encoder layer. This enables each position in the input sequence to attend to all other positions in that same sequence, directly capturing those internal dependencies. And finally, the decoder also uses self-attention layers, but with that crucial masking we talked about to prevent it from attending to future positions that it's currently generating.
Right. Makes sense. So this self-attention mechanism seems particularly novel and powerful. The paper even dedicates a section to explaining why self-attention. What are the main advantages they point out?
Yeah, so they compare self-attention to both recurrent and convolutional layers based on 3 main factors, which they summarize in Table 1.
Yep.
The first is computational complexity per layer. Self-attention has a complexity of big O of n squared times d, where n is the sequence length and d is the representation dimension.
Okay.
Now, this is actually better than recurrent layers, which have big O of n times d squared, when the sequence length is smaller than the representation dimension, which is a pretty common scenario in machine translation, especially when you're using things like subword units. So for many practical applications, self-attention can be more computationally efficient.
That's a significant point in terms of scalability. What's the second advantage?
The second is the amount of parallelization possible. This is measured by the minimum number of sequential operations required. Self-attention needs only big O of one sequential operation. This means that you can process all positions in the sequence in parallel.
Okay.
Recurrent layers, because they're sequential, require big O of n sequential operations. This ability to parallelize is a huge advantage, especially when you're leveraging modern parallel computing hardware like GPUs. You get much faster training times.
Absolutely. Harnessing parallel processing is crucial for training those large, effective models.
Mm.
And what's the third key advantage of self-attention?
The third advantage is what's called the maximum path length between any 2 positions in the network. A shorter path makes it easier for the network to learn those long-range dependencies. In self-attention, the path length is a constant big O of 1 because every position can attend to every other position in a single step.
Gotcha.
Recurrent layers, on the other hand, have a path length of big O of n, and convolutional layers have big O of log base k of n, or big O of n divided by k, depending on the kernel size and network depth. This constant path length and self-attention is a major reason why the transformer is so good at capturing those long-range relationships, like maintaining context across long passages of text.
Okay, so it's more efficient in certain scenarios, it's highly parallelizable, leading to faster training, and inherently better capturing long-distance relationships. That's a powerful set of advantages. Now let's move on to the practical side. The training and the results. What kind of data did they train these models on?
So they focus primarily on machine translation. They use 2 widely used data sets. The WMT 2014 English-German dataset, which has about 4.5 million sentence pairs, and the WMT 2014 English-French dataset, which is bigger, with around 36 million sentence pairs.
Okay.
They use byte pair encoding for the English-German task and word piece vocabulary for English-French. These are ways of breaking down words into smaller subunits.
Okay.
This helps the model handle rare words and reduce the vocabulary size. And they organize their training data into batches based on approximate sequence length for efficiency.
And what about the hardware and the duration of the training? That's always a key factor.
Yeah, so for their experiments, they used machines equipped with 8 NVIDIA P100 GPUs. The base transformer models took about 12 hours to train for 100,000 steps. Their larger big models needed around 3.5 days for 300,000 steps. They actually highlighted in the paper that this training time was significantly less than many previous state-of-the-art models. They used the Atom optimizer for training, and they had a specific learning rate schedule that included an initial warm-up phase.
Now, they also mentioned using some techniques to prevent the model from overfitting the training data. What regularization methods did they employ?
So they used residual dropout. That's applying dropout to the output of each sublayer before it was added to the residual connection and then normalized.
Okay.
Dropout is a technique where you randomly set a fraction of neuron activations to 0 during training.
Gotcha.
And they also applied dropout to the sum of the input embeddings and the positional encodings. The dropout rate for the base model was 0.1. Additionally, they use something called label smoothing, which slightly reduces the model's confidence in the correct label during training.
Okay.
This might sound counterintuitive, but it actually helps the model generalize better to unseen data.
Interesting. And the results were quite impressive, right? They reported state-of-the-art performance on those translation tasks.
They were. On the WMT 2014 English to German task, their big transformer model hit a BLEU score of 28.4. To give you some context, this beat the previous best results, including ensembles of multiple models, by more than 2 BLEU points. That's a big deal. On the English to French dataset, the same big transformer model achieved a BLEU score of 41.8. And what was particularly noteworthy is they got these results with significantly less training time and computational resources compared to the leading models back then, which they detail in Table 2. Even their base model was outperforming previously published single models and ensembles with lower training cost.
That's impressive. The paper also delves into various experiments, exploring different configurations of the transformer, summarized in Table 3. Were there any particularly interesting insights from these abletion studies?
Yeah, they varied a few things systematically, like the number of attention heads, the dimension of the keys used in the attention, the overall model size, and the dropout rate. They found that having multiple attention heads was crucial, but there was a point where adding too many didn't help and could even hurt performance slightly. Reducing the dimensionality of the keys negatively impacted performance. Larger models, unsurprisingly, performed better, and dropout was consistently effective. Interestingly, they found that using learned positional embeddings yielded almost the same results as their sinusoidal positional encodings.
Positional encoding is a fascinating aspect. Since the transformer processes all elements of the sequence in parallel, it doesn't inherently have a sense of order. How do these positional encodings provide that information about the position of words in a sentence?
It's a great question. It's a clever part of the design. They add these positional encodings to the input embeddings at the bottom of both the encoder and decoder stacks.
Okay.
These encodings are vectors of the same dimension as the word embedding, so they can be added element-wise. They use sine and cosine functions with different frequencies to create these encodings for each position in the sequence. Their idea was this would allow the model to learn to attend to relative positions through linear combinations of these sinusoidal functions.
Yeah.
Now, they experimented with learned positional embeddings and found similar results, but the sinusoidal approach might generalize better to longer sequences.
That's a really elegant way to incorporate sequential information without resorting to sequential processing. Now, beyond the impressive results in machine translation, the paper also demonstrated the transformer's capabilities on English constituency parsing. Why was that significant?
Right, so constituency parsing involves identifying the grammatical structure of sentences, and it's a task with inherent structural complexities in the output.
Okay.
Traditional RNN-based sequence-to-sequence models struggled here, especially with limited data. The fact that the transformer, without major modifications, could achieve good performance on this, even outperforming the well-known Berkeley parser on a smaller data set, showed its ability to generalize beyond sequence-to-sequence generation to tasks with more intricate output. As shown in Table 4, when trained on larger data sets, it even surpassed some specialized parsing models.
Finally, the paper includes attention visualizations in the appendix figures 3, 4, and 5. What did these visual representations reveal about how the transformer works?
These visualizations provided a look into the attention mechanisms, allowing researchers to see where the model was focusing when processing different parts of the output.
Okay.
They showed examples of attention heads successfully capturing long-distance dependencies, performing what appeared to be anaphora resolution, and behaving in ways that correlated with the syntactic and semantic structure of the text. For instance, one visualization showed that when the model was translating a sentence with a pronoun, an attention head focused on the noun that pronoun referred to.
Okay.
This gave researchers a clear sign the model was learning to understand these contextual relationships. The visualizations highlighted the interpretability of self-attention, suggesting that different attention heads might be learning to perform different roles.
So to bring our deep dive on attention is all you need to a close, what would you say is the most crucial takeaway for our listeners?
The key innovation was the transformer architecture itself. By relying on attention mechanisms and ditching recurrence and convolutions, it marked a major change in sequence transduction.
Right.
It offered not just better translation quality, but also big advantages in parallelization, leading to faster and more scalable training.
And for you, the listener, the impact of this idea can't be overstated. The transformer has become fundamental in AI, particularly natural language processing. Its ability to model long-range dependencies and suitability for parallel computation have paved the way for advancements we're seeing in language models, conversational AI, and more.
And this leads to an interesting thought. Given the transformer's success in modeling relationships without strict sequential processing, could similar principles be applied in other areas beyond language? What about things like computer vision, where understanding the relationships between different parts of an image is crucial, or time series analysis, where dependencies across time are key?
Definitely some fascinating possibilities to consider. If you're interested in the technical details, we highly recommend checking out the original paper and the code. It's a really influential piece of work. Thanks for joining us on this deep dive into Attention is All You Need.